All right, we are live.
Perfect.
Hi everyone, I'm really excited to interview Iro Armeni. She's a postdoc researcher at ETH Zurich. She is conducting interdisciplinary research between AEC and machine vision. Her area of focus is on automated semantic and operational understanding of buildings throughout the life cycle using visual data. I really admire Iro's work. I have been reading her research papers. I first got to know about Iro last year from AI for AEC symposium, and then I also followed her ETH Zurich course. I was like reading all the slides, and it just feels great to interview you and host you. So we have a lot of exciting content lined up. So without much ado, thanks Iro for joining for this session.
Thank you, Meyer. It's a pleasure to be here.
Yeah. So before we dive into technical questions, I have some uh, personal journey questions. So just to give a background for this question, you did diploma in architectural engineering, engineering in architecture and digital design, MS in computer science, PhD at Stanford in C, and also minor in CS. So I also have like some multidisciplinary. I moved from civil engineering to architecture to software development and AI. So like, can you share like what was the evolvement of your career interests? Like, were there any like points or realizations that were crucial in shaping your career trajectory?
Yes, there were actually. So yeah, as you pointed out, I started as an architect. I always knew I wanted to become an architect, so I had, as a kid, a very kind of predefined career path in my head that this is what I will do and focus on. And so I did my diploma in architectural engineering, and it does have engineering parts within it and civil engineering parts within it, very small, but we do understand these things during that diploma. Then I went more into the digital design aspect of it and understand how we can use generative algorithms in order to create forms. But until that point, everything was about the forms. But then I was doing my master's in Tokyo, and I was going to continue there for a PhD. But unfortunately, the tsunami hit back in 2011, I think it was. So at that point, I was just wrapping up my master's thesis, and I decided that after that, I won't continue to stay in Tokyo, but I will just go back and figure out my next steps. So while trying to figure out what I will do next, I started working at my hometown. It has a lot of historical buildings, it has a lot of UNESCO monuments, and I started working there as an architect. And that is where, in practice, I found the issues and the passion that kind of brought me to where I am right now. There were different points that actually, pushed me to this direction. I have to say that before that, I knew nothing about AI or, very minimum exposure to computer science, just in terms of utilizing a computer and designing and rendering and stuff like that, but not really more hardcore computer science stuff. And while working as an architect, I decided to do a master's in computer science. I thought it would enable me to do better coding, understand better some things, potentially give me an edge if I wanted to do afterwards a PhD. Probably in digital design, still I was then at that kind of point in my life. So while working as an architect in that more kind of historical city, I had to do a lot of renovations, and I was also working in a museum that is a UNESCO monument, and I had to deal with a lot of okay, what is the as status of my building? What do I have right now in my hands? And every time we would go around with a measuring tape, because we didn't have any other equipment at that time, that is the best we could do, and go around and take measurements. And there were nowhere, there was not a good documentation of the building. We never knew what we had in our hands. taking notes was always very difficult, and it gave us very little information of what was going on. And in addition to a couple more things that were going on that I will be happy to talk more about, but I don't want to make this super long, I started figuring out that there should be a better way to understand what we have in our buildings. This cannot be the way. As an architect, I want to do creative things. I don't want to spend half of my work trying to figure out what is the status for me to do a new design. Then I got, by just looking, I found about photogrammetry, about laser scanners, but also about the issue, okay, even if I get the 3D scanning, which gives me more geometric information in my hands, what can I do with it? I still need so much manual intervention in order to make it something more tangible and information that I can afterwards use easily. And this is more or less how things happened. I applied for a PhD, and here I am, still working on that.
That's amazing. Like that frustration or tediousness of the task was like the core motivation. So I want to know, like, was coding very natural to you, or you had like initial struggle when you were learning it?
I think I still struggle, as everyone. I can't call myself an expert coder, not at all. I think my collaborators could be able to attest to that. But I can work with it, and thank God, there is always the internet that can help you find solutions in every problem you might have. I don't think I had a particular struggle with understanding how to use coding. We weren't really taught coding when I was at school. I mean, like middle school or high school, we never had this, apart from a very simple program where you were supposed, I think it was called Logo. There was kind of like a turtle that you could draw shapes around. So you would tell it, go forward by that much, go left by that much, rotate or whatever. So this was the only thing I knew about coding. But for some reason, I was never intimidated by coding itself. I think the hardest thing in coding is to just know what you want to code, not how to code it. Like, what are the steps, the functions you want to create? What do you want to solve? I think this is the biggest question when you want to code something. There are so many resources out there that the rest is more or less easier to do. But what kind of operations you want to perform on the data, that is for me is the biggest question to solve.
Yeah, that's a great insight. My next question is like, it's very evident in your career trajectory about your multidisciplinary integration and also in your research work. So according to you, what are some aspects of other disciplines that AEC industry can learn or adapt or integrate?
That is a very good question. And I don't think I will give an answer, but I don't think there is one particular or that is always set. I think it changes based on the developments, both in AEC and in the other industries as well. Definitely manufacturing has a lot to teach us of how they have introduced automation within them. But let's not forget the big distinction that manufacturing is a very staged environment. Whereas usually in the AC industry, we have something that's more chaotic, there are more stakeholders involved. So there are different considerations we have to take into account. But it still, I think, has some things to teach us of how did they transition from something more manual, something more automatic. And then we also have the case of medicine. I think in last year's colloquium, we saw Serena Young coming and tell us about their research that they do in the health department and all about using vision to understand actions and in terms of the doctors and the patients, etc. So I think we can still learn even there, where there is a chaotic environment and there are a lot of people involved and a lot of privacy issues, for example. There are all these other domains that are adjacent in a way to the AC industry, like law. They are trying to do things with AI, and I think they're doing an admirable effort over there. And we can probably start integrating these within the AC. Of course, we have to be patient. We have to be careful of how we do all these integrations. But I see a lot of things that we can learn from them as well on how they are doing the integration. These are just 3 examples. There might be more, but I'll just stick with them.
Yeah, and like I was a bit also surprised because in the colloquium, it was the first time I saw where not only for AEC, you invited all other experts from other industry to share and how we can learn. And that was quite insightful, how they are how they are solving the problems faced in their industry. So now, before we move deeper into the 3D scene graph paper, um, I would like to share the screen. So you can see the Chrome uh,
Yeah,
interface. Yeah, awesome.
screen. Yes.
Uh, so my next question is, like we see your research work from like 2016 building parser to in 2019 3D scene graph, and this is like few of your selected projects. So what were like some key highlights you would like to share in this research work?
In the research path that I've gone through 2016 till 2019.
Mm-hmm.
Well, I want to say that, well, the first thing I want to say is that research is hard. And particularly when you have to deal with data, when you have to, with like collecting new data, creating new data, it's something that it takes a lot of time. And it needs a lot of consideration. It's not so I think that that is what I can try to do with my work, to try to, I mean, I've learned a lot since 2016 to 2019. I've learned so much about how to deal with data, how to annotate, how to think of data sets, about benchmarks, about metrics, evaluation and validation. And these are things that I try to say every time, even to students, or if I talk to someone from the AEC industry, that we need to set better ways of understanding what we have, of setting questions and of measuring the answers we want to get out of these questions. Otherwise, we cannot really understand, measure how good or not we're doing. At least I see that both in practice, but also sometimes in the research department of the AEC, that these are things that are not as well defined as in the AI domain. And I would love to see this transitioning better into us as well.
Got it.
As for, yeah, and as for the specific path and how things started, I started with building parser, which gives us a semantic understanding of point clouds, kind of a 3D Lego world it gives you as an output. I wouldn't call it a 3D model, but more like a 3D Lego it can give you out of that. And then we continued into understanding multiple modalities. I think the work culminated with 3D scene graph because it allows to create the to represent the ASIS information in a way that it's understandable by humans and machines, and it has a lot of information that would be necessary different for different functions and processes in the AEC industry. So within one place, you can include all this information instead of having something separate for architecture, something separate for construction, etc. I know that specifically that paper, because it was submitted to a more computer vision conference, it doesn't explain how it can necessarily be used in the AEC industry, but this is something I'm working on, and I hope that in the next months I can have something that would be a little more detailed and explain a few things about that.
Awesome. So in the paper, scene graph paper, 3D scene graph paper, I saw that you mentioned that this paper was the inspiration and the starting point for your paper, which was like published in 2016, which connected language and vision. So from my understanding and research, like solving problems in 2D is at a whole another issue, but 3D makes it way more complex. And you took it from this 2D inspiration and to your 3D scene graph. So what were like some major challenges while developing this research paper?
Yeah, well, first let me say that I just think that the problems that one has to deal with in the 2D and the 3D domain are just different. I don't think that one is necessarily more complex from the other, because 3D has some advantages with respect to 2D but make 2D more challenging to solve, whereas in 3D might be easier, and vice versa. So I wouldn't necessarily call it more challenging. But the extension was not 100% straightforward. There were no humans inside the data that we were dealing with, at least. So if you look at the visual genome as itself, at the kind of data they represent, it has a lot of actions that are happening between humans and objects in the scene. And that is mainly their, in a way, the focus, right? So there is, as you see here, I don't know, a lady holding a camera. I don't remember what I saw, but they kind of explain this kind of information within the image, the visual data, and that is something we didn't have. However, the structure of the way you would represent the information is similar. So you still have the nodes of the graph, which is mainly the important, let's say the objects or the humans in the case of the 2D scene graph. And then you have attributes for each of these objects. And then you also have relationships between these objects. And in our case, the relationships might not be actions, but they are different things that depending on what objects you are looking at and what are the possibilities, what kind of relationships you can query between them essentially. Yeah, so the structure is similar, the kind of information we ended up portraying is different. So we ended up with including, since we're talking about a three-dimensional space and a building, we ended up including multiple aspects of it. And we did that by having it in 4 different layers, essentially, introducing the building, the rooms, the objects within the room, and then adding the camera as part of this entity, and allow to essentially do things with by introducing the camera there. You can do more visual things, more visual tasks within this environment, train or capture more data, etc. And then the relationships, as I said, were defined based on the attributes and the objects that were within the scene. And yeah, I don't know if you want to go into more details, but this is more or less the differences that I would say between the two.
Yeah, I think that explains really well. And um, just just for the viewers who are knowing this paper first, so you take input 3D mesh, camera parameters, and panoramic images as input, and outputs like a 4-layered scene graph structure where, like as you can see, first layer is building, rooms, objects. Yeah. So from the paper, what I found really interesting was uh, the two proposition of framing and multi-view consistency. So if you can, uh, maybe I'll take a step back. So if the way I understood was from different camera uh, images, you you saw like you adopted mask RNN to do to find the to do object detection and segmentation, and then in the theory it was like you the center of the object in the center was weighed more, and then you projected that pixels into the 3D mesh to identify the object in 3D space. So
More or
uh,
less.
sorry.
More or less.
I see. Yeah, so um, I wanted to ask, like, there was one part in the paper where you were discussing about what if there are some objects which are half in the frame and it's not included. So how do you deal with those kind of objects?
Yeah, that's a good question. So the first point here is that the input to this methodology that we created, which is semi-automatic in order to provide the 3D scene graph on data, mainly for labeling purposes. I mean, like annotations, providing annotations on the data set. The input is a 3D equirectangular image, which means, sorry, a 2D equirectangular image, which means it's a 2D panorama, in other words, which has a 360-degree view, right? So you have access to most objects, and depending on how you decide to sample your smaller frame, like the ones we are like rectilinear frames, we're able to take, let's say, with a regular photo camera on our phones, you can decide how you want to sample it. And depending on how you sample it, you will see more or less of objects, of an object within this frame. And that is what framing is. Essentially, we're trying to use the data we have in our hands, which is a 2D panorama, and try to find a way to better sample these rectilinear frames that we're going to use afterwards. The way we went like that is because when we did that paper, segmentation on panoramic images was not that broadly used. There were some first papers on that, but they were focusing on different kind of images, different kind of data. And what we wanted, since we were trying to annotate an existing data set, was to do something that was faster, and we already had some pre-trained networks on it. And the best one at that point on semantic segmentation, instance segmentation, was the Mascar CNN, which takes as an input rectilinear images. So we needed to find a way to somehow convert the 2D panorama in those rectilinear images in a way also that we can have as good results as possible. As you pointed out before, there are issues with objects that are at the corners of the frame and you are not fully visible within the panorama, or they're too far away from the camera lens. These create the most problems. But by doing the framing operation here, we're at least able to fix the issue of having the object as much as possible at the center of the frame and nicely cropped. Like you have a little bit of context around it, but you can also see the object nicely and zoomed in. This is the best interpretation can give of that operation. The way we sampled those rectilinear frames is not something that is super intelligent, I would say, at this point. And I'm sure that like, I can think of other ways that one could make it smarter. But at this point, it's just densely sampled rectilinear frames with different size and different rotation, field of view, etc., with different essentially camera parameters on the panorama. So we have all these overlapping smaller frames that we then feed into Mascar CNN, and we get all the predictions. And the bottom line there is where you said like the center prediction is weighted more. The reason that this is happening is because, as I said, we are densely sampling rectilinear frames. And as a result, we need to somehow disambiguate between pixels on the 2D panorama that have more than one vote, that have necessarily been segmented and found as objects in more than one rectilinear frame from Mascar CNN. Sometimes, like the most of the times, the votes are for the same semantic category, like, oh, it's a chair, oh, it's a book, or whatever. But there are some times that there are conflicting, especially as I said before, if in some of those frames, these objects were found at the edges, they will be most probably wrongly detected. So we need to find a way to fix that. So we have this weighted voting scheme to help with disambiguating conflicting labels. This is what the framing is.
I see. So, so mask RCNN, like you use that pre-trained model, so it has like some of the common object classes. Were there any like objects in the AEC space which were not part of the like pre-trained class, and you had to do like transfer learning and train or something?
There are a lot of labels that don't exist in the AEC industry in this data set that we used, in this network that we used, but we didn't do anything more to get them. What we used is a pre-trained network from Mascar CNN that is trained on the COCO dataset. The COCO dataset is one that has a lot of common objects within interior and exterior of houses, of buildings. We focused on those interior that would exist in interior because we're looking at the interior of houses. That's what most of the data we had in our hands was. But they do not have structural elements, like they do not have the floor, the ceiling, the columns, etc. These kind of labels exist in an extension of the COCO datasets, which is called COCO stuff. We try to train the Mascar CNN on the COCO stuff data set, but we were having issues. So we ended up not including that, and we stayed only with the Coco data set, which means we have mostly annotations for objects or appliances within the building and not about the building itself. Which of course
Got it.
it's a yeah, not great, but for the purposes of demonstrating things, it's still good enough.
I see. And for multi-view consistency, I'm just wondering, like that there are a few times when you do like object detection, it gives like wrong class or there are some errors. Like, were there any like outlier or like error cases when you were combining it?
Yeah, of course. There were definitely error cases. After, let's say, framing, we still had issues, and that's why we did the multiview consistency. And that is also apparent if you look at the quantitative evaluation, qualitative as well, but let's stick with numbers. In the quantitative evaluation, we try to see the performance of the algorithm both before any of these mechanisms, after framing, and after framing and multi-view consistency, we saw that there was a consistent increase in the performance of the algorithm by introducing all the steps. Now, let's not forget that the performance was not near perfect because we are dealing with a pre-trained network that has never seen this data before. It was never trained on any portion of this data, a completely different data set. And although, yes, it is another data set with images, that has nothing to do because the statistics are very different, the noise might be different. There are a lot of issues that do not allow necessarily to easily just transfer one pre-trained network and one data set on another. However, Mascarcinen did, I think, because it was very well trained, and the way they are doing the train does allow for a lot of to augment the data in a different way, to look at the data in a different way. It had a very good performance on this unseen data. Still, though, not perfect. If you see the quantitative evaluation, it's not good, but it was a big step towards the point we wanted to make it. It's the semi-automated annotation pipeline. Yeah, that's why we did the multi-view consistency, because we were able to have these 2D panoramas that were better than just results on the rectilinear frames, but still there were issues. There were issues on the category of the segmentation mask. Like instead of a chair, there could be a bed. I'm just saying right now. But also on the how well it was segmented, specifically in this kind of like video that's playing on the screen. This big green blob that you see on the panorama, it's a table and the mask is kind of like flowing and leaking on the floor. And we're trying by the multi-view consistency, not only to fix labels, but also to fix these issues with the segmentation pipeline.
I see. And before reading this paper, like I was not aware about like Gibson Simulator, and like it was can you elaborate like what's the purpose of that and what people can do with that simulator?
Absolutely. It's a work that originated at my lab at Stanford, at the CS lab at Stanford, where I was a PhD student at. And it's essentially a physics simulator for training agents for visual perception tasks. And it had this big database of 3D spaces of real world scenes like the ones you see right now on your screen. These are from the Gibson database, but there were no semantics. And one of the reasons we wanted to work to demonstrate the 3D scene graph on the Gibson database is also to be able to provide the semantic annotations for other research purposes. And one of the other reasons is that 3D scene graph could be beneficial also for a lot of such agent tasks, agent-related tasks, because the agents then can learn on the semantic abstract space instead of the metric space directly. And that can be very helpful when you're trying to generalize your task to a very different space that you've never seen before. So these were kind of the two main reasons that we decided to do this on the Gibson database.
Got it. I would like to go a bit deep. So the way I understood is once you do mascard CNN, you identify the objects, and those objects become nodes, and you do it for every floor. And like how uh, I read that there was some like ways you were getting like volumetric dimension also of those objects in the room. So if you can elaborate on like the whole trees like graph structure, like a high level overview about how it's done.
Yeah, absolutely. So, as you very well said, the objects that we are identifying are become nodes inside this graph. That is not only after mass processing, but all after framing a multi-view consistency. So it's like the end of the semantic of this automatic annotation pipeline. There is a verification step as well for some of these data trees that we created with humans in the loop, where they could verify and edit or re-annotate from scratch if they couldn't edit the what we found as an automated output. So once we have this in our hands, we can go and start populating the 3D scene graph. For the rooms, we didn't use something new. One could follow a similar pipeline, but what we did was to just use the way that the rooms were segmented in the building parser paper. So we used that way to do it. And we manually verified the result of the algorithm, so to make sure it's correct. The also the functions of each room at this point we manually created them. We tried to do something more automatic, but again, because of the difference in the data, the domain gap that exists between different data sets, the pre-trained networks that we found, for example, on MIT Places, which is a data set that contains images with functions, what is the scene essentially category, did not perform that well to allow us to actually use it from scratch. So we decided to manually annotate that for the purposes of this data set. Otherwise, one could definitely do that if they could take care of the domain gap. So yeah, that's how we created the nodes for the rooms. And then the objects, we take them from the semantic pipeline that we saw before. And the camera also can be any kind of camera, which is like the top layer, or could be, in this case, we also can have the cameras that correspond to the 2D panoramic images that come with the Gibson database and the ones that we used to do the semantic annotation. Then we have the attributes. So now we put all the nodes, all these like circles that you see on your screen, and then we had to start populating the attributes for each of them. And now, depending on the layer, if it's a building, if it is an object, you want to have different attributes that describe that. For example, for objects, you have material, you have texture, you have volume, you have area, you have size, and some action affordance that we kind of predefined as to what actions it could enable this object. And we started populating that. Again, some of them were manually populated just because we couldn't find pre-trained networks for that. But hopefully, by providing this data set as well, more research can be done to fix this domain gap and be able to have more results on automated material recognition or texture recognition. And we used existing other data set classification in order to do it. So we used the dictionary of the data set. I'm sorry, I don't remember the name right now from, by heart, for materials and for texture. There exist a couple of data sets out there that we used to decide what kind of categories we'll have for each of those cases. And then the other were analytically computed because we have a 3D space, we have the semantics all calculated, so we can find the 2D area of an object, we can have the volume of it, which we found by doing a 3D convex hole mostly. We can voxelize it, we can find its color if we wanted, we can do a lot of things. And this is how you we populated the attributes. Learning where we could, manually where there was nothing else to do, analytically where it was possible. And then there are the relationships. And the relationship is not something that you could add necessarily to the 3D scene graph. It's something you have to compute on the fly depending on what you need to query, what kind of relationship you care for. And we have a code that we released to the public to help with that. And it's about, for example, if two objects are in the same space, if a camera location is helping one object occlude another object, if two objects have the same volume, the same spatial location with respect to a camera, like where are they located, is one in front of the other, etc. So there are different things you can query, and we have some list of possible things you can do. A lot more can be done. We had just to set somewhere define the scope.
God. Yeah. So uh, the two things I was a bit confused was like, how are you discretizing like each volume of room? So I'm not sure, like, does mask RCNN provide like room as a single instance, or ceiling, wall, or floor as different? And how do you like combine the whole room?
Right. I think I mentioned it for to get the room instances, the room segmentation. Essentially, we use the building parser way of getting the room parsing that fits in that method. Masker CNN does not provide. Masker CNN could provide, but the COCO dataset that we used, where the Masker CNN was pre-trained on, does not have semantic categories such as floor or walls or ceiling. This would be part of COCO stuff, which we weren't able to use. So in that sense, we have the volumetric aspect from there. Yeah.
Yeah. Maybe I'll read the building parser paper, and
I'm
that will
happy to explain.
help. Awesome. So before we move on to the code, is there anything else you would like to share?
Well, I mean, I would definitely like to also like hear your opinion how you saw this paper with respect to the AEC industry. I wanted to, I have my own ideas of how and why this was needed, but I would love to hear your opinion if you have any thoughts on it.
Oh, thank you. I think like I have read a lot of research papers ranging from GAN, reinforcement learning, but there are very like lesser papers on like using BIM and like a graph structure. And this was one, and I also read one from a University of Singapore, where they were using BIM and graph neural network. So I think this has a big potential. I'm still wondering why it's not largely accepted, and why people are not developing applications out of it. That's why like I wanted to review the code so more and more people can do like quick testing and deployment, and maybe use it in any of hackathon or something.
Absolutely, that would be great. And yeah, I mean, listen, 3D SIMGRAPH is, I found it that it would be a good way to represent things, but one could create any kind of 3D SIMGRAPH they wanted at the end of the day, right? So that's maybe one of the reasons. But I do feel that there is a lot of there's a lot of value here, especially where with some specific elements that are part of it. So I personally think that this representation could help even better than a building information model, which again, it's still a graph, it's a tree structure as of data representation, but it's not as flexible as the 3D SIMGRAPH, potentially due to the tools that exist that deal with BIM. I'm not sure, but I definitely can understand the flexibility and the easiness of the 3D SIMGRAPH with respect to a just standard BIM model.
Yeah, I just had a thought right now. It would be really cool if there's like a plugin or in Revit or Rhino, which can does like this computation in the backend, so people can integrate it in their workflow. But one thing I would like to share is like I have read other papers, and quite a few like have cited 3D scene graph paper, and it just makes me feel like proud of the EC community, that even other computer science community like thought that 3D scene graph is the need, and you guys like took the risk and like solved a great problem. So amazing job.
Thank you, Mayor. The collaborators. Yeah, it's a team. It's an effort team. It's not one person. So yeah.
Got it. So now we will like do like a review of like some important aspect of the code. So uh,
So one, as we go in, dive into that, there are two important things here. The first one is that there is a code that once you have a 3D scene graph, like if you download the data set, is the one that can actually take this raw data from the data set and create the 3D scene graph for you in the structure that we provide in the code. And there is also code to query for relationships, etc., etc. So there is that part. There's also the other part where it's the automatic part of the same automated pipeline where it creates these object semantic annotations from the 3D mesh and the 2D panoramic images. So there are these two aspects.
oh god, I was not aware about that. So that's good to know. So would you like to talk about a particular segment of the code, or yeah, or I can give you screen sharing, whatever you prefer.
Yeah, I can actually share my own screen. I think that would be easier for me to go around.
Hmm.
Could you enable me to?
Oh, I'm really
Okay, that's great.
sorry.
That's okay.
Yep, you might be
Okay.
able to do it now.
Yep. Okay, you can see my screen, right?
Hmm.
So yeah, let me remind myself as well. So these are just some tools that would enable someone that already has downloaded the dataset to run the code. Um, so let's start over here first. This is the dataset structure. One should always read the README file before doing anything else when dealing with a new code. New code repository. So we see here the data structure. This is what one would expect to see under each of these layers. So for the building, you have this information in your hands. For the room, for the object, for the camera, you have all this information. Here are the tools and dependencies, where here we explain that there is this loading function, which requires this kind of Python 3.5 and then try mesh and peel. And you can run this function with the bash script load.sh. And this would essentially call the function that creates the 3D scene graph out of the raw data in the database. And then, of course, is the automatic labeling pipeline, which I said is the second part of the full repository. And you have information about framing, about multi-view consistency, and of course about generating the raw data structure that we also have in our data set. And then as for the automated labeling part, we do not include, of course, the mask RCNN that we use. This is something that we point where you could download it, but we have here the first step of framing once you have the panoramic images in order to get the this deep, dense sampled rectilinear frames. Then there is some kind of detection step. You can use mask RCNN, you can use any kind of other detector. Then you have the multi-view consistency step, and finally the 3D scene graph generation. So this is what the code consists of. I wanted to also say, which is part of the paper, that we've tried both with mask RCNN and with another detector, BlitzNet, which is real time, which means it provides way faster results than what mask RCNN requires for inference, essentially to process one rectilinear frame. And we did see that these two robustification mechanisms of framing and multi-view consistency on the datasets that we had. Again, the BlitzNet was trained on the COCO dataset and directly applied without any kind of additional training on the Gibson database. We saw that there was an equivalent increase in the performance, which shows that it's not only it doesn't rely necessarily on mask RCNN. Even using another algorithm, it's also could also, these two robustification mechanisms can help. So one could use whatever they have in-house, or if they can find something else, they can use something else for it. Hopefully it will also work for other kind of object categories. We haven't tested it, but hopefully it can have the same output as well. So yes, inside source, we have the framing, the multi-view consistency, and the 3D scene graph. And one thing that I think it's important to know is that it's also, I guess, downfall of the dataset as well. When we do the multi-view consistency, and I guess I can just show it maybe here. We do the multi-view consistency, and we get all these. Essentially, the output should be the different semantic instances of each object category. So 2 chairs, 3 tables, 1 sofa, 1 bed, etc., whatever exists in the scene and was able to be identified. However, during the processing from the 2D panorama to the multi-view consistency, we lose the notion of instances that were found in the 2D panorama. And that means that we are processing everything as non-instances. Non-instances means everything is a chair. There is no 1, 2, 3, 4. Everything is just chair, chair, chair. There is no 2 beds. It's just bed. Then we are using the found segmentation, this plain segmentation, to find the instances. And we're doing a 3D clustering on that. But there are some issues there, some geometric, some have to do with the semantic segmentation on the first hand, and the instances are not perfect. So sometimes you might see 2 chairs that are actually labeled as 1 chair. And that is an issue, but it's something that we cannot necessarily solve except if there is a manual way to fix that. And in some cases we have fixed in the manual way, but since the database is not completely verified, there are issues where this persists. 3D clustering and clustering in general is a difficult problem that is still into research. And I'm sure there might be more intelligent ways to approach it than the one we had here. But and this is still an open domain for anyone who wants to look into that. I guess this is a downfall. I have to explain the limitations. So I'm not sure what exactly we can see in the code. Maybe we can see where we can see the loading function. I think it would be easier. So in the loading function, this is a Python file, right? So you always begin with explaining the dependencies. I don't know in how much detail I should go, but I'll just say that. And then here we have defined a class for each of the different layers within the 3D scene graph. And each class has its own kind of attributes in a way, which is the attributes that we have for that explain this layer. So we have the initialization aspect here, and then a function that can set attributes or query attributes within this specific instance of the class. When you initiate a building class, then you would be able to query for an attribute or to set an attribute, the value of an attribute. And similarly, you have the class for the room, for the objects, again, setting and getting attributes, and the camera as well. And then over here, you're just loading the file. You define the paths where you want to find it. But before we go that, there is a main function. This is where the algorithm starts. There are some arguments that need to be set. These arguments, one can just add them manually in the terminal where they would call this function. But in our case, this is handled by the bash file that we said that you would prompt this file over here, this Python file. And then you can decide if you want a verified graph or an automated graph. For those spaces that we have verified the output of the automated method, we provide both. For others, there is only an automated graph available. Here you essentially initialize the variables for the different paths that were passed through the argument parser. And over here, you start looking into the 3D scene graph and querying and essentially calling the 3D scene graph function above. And if you decide that you also want to visualize things, here you can export either OBJs or images for these rooms for the results. Here is the code for exporting segmentation PNG, essentially images, for exporting segmentation OBJs, essentially wavefront files, We go above. Here is for instance segmentation, which means that I have tier 1, tier 2, tier 3, and usually they would have a different color. And over here, we have the loading function. So it just loads the file, which is an NPZ, which is a compressed NumPy file. And you set all the building attributes, and you start then going into rooms where you set all the unique room attributes, all the rooms that exist there. Then you go over the objects and you set those as well. And then you set the camera. And if there are any panoramas as well, you also can load the panoramic instance segmentation, etc. on it. And I have to say also that after we finish the semantic segmentation with the framing of the multi-view consistency and potentially the verification, we back project all this information back on the panoramic images. So the segmentations we offer on the panoramas are consistent with what you see on the 3D space as well. So one could use them too. You get as an output the building, which is that class that contains all the layers under it, as well as the panoramas that contain the semantics and instance segmentation for this specific panorama. Yeah, and the rest of the functions are just auxiliary functions, such as load a palette. It's a color palette just to give a color to specific instances. Here you have the COCO dataset classes that we were handling. It just gives essentially a way to go from a label to an index and specific number and vice versa. Yeah, the rest, as I said, are exporting functions. So this is the code to bring up the 3D scene graph given the NPZ files of the database. And once you have that, you can, I think it's in here, you can query the relationships. Maybe it's under here, relationships. So you can find the parent room of an object, essentially where an object exists. You can get the camera's parent room. I think this information, it's a very simple relationship that I think exists already in the database. But if somebody wants to use it for creating a different 3D scene graph for something that's not existing in the database that we provide, they can call these functions to quickly get these room IDs for example, these different nodes. You can identify if two objects exist in the same space or not with this function over here. So it provides as a return if it's true or false, whether they're in the same room or not. And here you can get all the element IDs, essentially, or the nodes of objects that exist within a room. For each of these functions that you see, there is always a description of what they do, as well as what it requires as an input and what it gives as an output. This one is rate mesh intersection. Essentially, this is used when you want to identify, when you shoot a ray from the camera, for example, to reach a point or on the mesh somewhere in 3D space, and you don't know where this point is. You want to find how many maybe surfaces intersecting, right? Is it behind the wall or in front of the wall? Is it actually intersecting a wall or not? So in order to do that, with respect to the mesh object that you have in your house, the 3D geometry, you know to do a ray tracing, that's what it's called, in order to find where it ends up, in which surface, and how many surfaces maybe it's heating in its way outside of the building. So this is what thesis does, and it's used to be able to identify all the things, such as an object is within one room or not, and which others are within which rooms, etc. It's also used for being able to do a model segmentation that exists in the papers and experiment, where given a specific camera and an image, you want to identify the model mask of an object, which means which parts of it are visible and which are not within the specific frame you're looking at. This exactly does this job of getting the model mask. And this one, get to object occlusion. It means that given a specific camera pose and two objects, you need to tell me which parts of the second object are occluded given the first object. If they are occluded at all, hopefully they are, or if that's what you want. And then there are, of course, the other relationships that one could query. The spatial order. So given a camera location and a query object that you care about, is the other object in front, behind, to the left, to the right, or even like specifically with a quantitative measure, like it's 2.5 meters to the left, etc. So you can get a 3D vector out of it as well, but also a lexical, a verbal, essentially, understanding of spatial order, top, bottom, front, behind, or left, right, with respect to the query object. And then, of course, you have the relative magnitude, which would be magnitude in terms of volume, of area, or of size. So you can see, essentially you're comparing the attributes of these two objects and seeing which one is larger or smaller and by how much. And this is the three essentially attributes we have defined for magnitude, but there could be more if one adds more attributes to the 3D scene graph that could be related to magnitude, essentially larger or smaller. Yeah, and that's it. We had some experiments on the 3D scene graph. I think with that I would kind of conclude what I want to say about 3D scene graph. Go to the paper. We had some experiments on 2D images, because one might think, okay, why do I need to know the relative, like why it's not important to know the relative volume of two objects? It's super easy to calculate in 3D space. Well, it is, but if you want to do things at some point only on 2D images, for example, in 2D images, the size or the scale of an object is not really defined, because if, for example, over here at the back we have a big chair, but it's represented with so little pixels, such a small number of pixels in the image, that it looks way smaller than, for example, a chair at the front, even though the size might be bigger. So it's very, if you just count the number of pixels, it's not enough to understand which is smaller, which is bigger. This is something that we'll have to learn based on the 3D aspect of this object, like its 3D physical presence. So you can learn this information from the 3D space, but then you can do predictions on the 2D space. So for example, for relative volume here, given the query object, which is this one with the yellow volume, and the segmentation masks of all the objects that we care about, one by one, we were identifying if it's larger or smaller in volume. So you can see that some objects are smaller and some objects are larger, or over here, etc. And if you look at them, they do make sense of what you are getting as an output. And we also have the spatial order. So you can identify if something is in front or behind, etc. Something. And this is how connecting 2D and 3D world through the 3D scene graph really comes in hand. But of course, there are more complicated things you can do. But these were just some simple experiments that we wanted to try. Yeah, I think that's it. This is the model segmentation, where you're predicting which part is visible and which is excluded.
And you also have shared like the supplementary material for this paper.
Yes.
Yeah.
In the supplementary material, we have definitions more about the object, the attributes and relationships that exist within the 3D scene graph. We have the video that shows the details, which you can find also on the website, better definitions about all these. Semantic statistics and analytics, given these the 3D scene graph annotations that we have. For example, let me find, like we have again more experiments on this relative spatial order or relative volume that I discussed before in larger images so one can see. But in terms of the statistics, I want to show, for example, this one, which is the co-occurrence of objects. Essentially, you can find out what objects are usually found together in buildings. So next to a bottle, you would mostly find a sink and a cup and a chair or a toilet, etc., which means that a bottle would be most probably found within a kitchen or within a bathroom, right? And it does make sense. Next to a chair, you most probably find a tiny table. Next to the couch, I don't know, a chair, a book, a potted plant, etc. Next to a keyboard, a TV. I guess TV would also be any kind of monitor that you would have. And then there is the microwave somewhere that also says that there is a kitchen, like here. Next to the microwave, you can have an oven, a sink, a vase, a refrigerator, so things that are closer together. Of course, you can see the word toilet coming up here. That is because usually kitchens are very close to bathrooms for the pipes and all the mechanical and electrical and plumbing elements that we know as engineers. So that's why it comes up as something that you would find close to a microwave. Doesn't mean that they're in the same space. It's just closely as neighbors in 3D spatial distance, Euclidean space, without understanding necessarily walls, etc. So yeah, these are things that you can easily get out of it. And since we're talking about hundreds of buildings, I think these are coming out. I don't remember out of how many buildings, maybe 100 or 200 buildings. It becomes kind of an understanding of how we place things in spaces, and we definitely can learn more from that instead of just doing co-occurrences of objects, being able to even dive even deeper to how we utilize spaces.
Yeah, I could definitely foresee like some like design takeaways from this like analysis. Was there any like surprises or non-intuitive findings?
From the co-occurrences of objects,
Mm-hmm.
I would say that most of them make sense. Of course, we do have kind of like a limited set of object categories in our hands, right? So we couldn't do more, but I mean, a potted vase, a potted plant comes a lot. It seems that we really like to have potted plants in our spaces, because if you see this pink ribbon exists in most of the items. So that means that we do put a lot of greenery in our houses. Maybe that is one thing that one could take out of that. I don't have the green thumb, so you wouldn't find any in my house, but I guess other people really like it.
Nice. Yeah, I must say like the way like you explain the whole code walkthrough and this part, like it makes the whole implementation so much intuitive now, and like it really helps. Thanks a lot.
Thank you.
So I know we have reached 1 hour mark, so I had few questions. So if you have some
Okay,
time,
sure.
awesome. So do you have like a utopian or dystopian vision with AI application in AEC?
No, none of them. I'm somewhere in the middle. I'm not overly optimistic or overly pessimistic that things will just, AI won't take over the world in the sense of we're gonna lose our jobs, or there's gonna be transitions. AI is not gonna kill us. AI is not gonna take over the world. We are the ones who are in power of how we're going to define AI, and if we are doing things correctly, then and considering not only technological aspects, but all the socioeconomic factors and the people around us, I think AI can only help us go do better. And we should, yeah, we should not forget that. But as I said, humans must be included in thinking about AI. Humans should never be out, and humans can be the users, the ones that are going to be provided with information, the ones that are going to be interacting with AI, the ones going to be somehow impacted by it. We have to look at all the different levels and understand about it, even if we're developing an application only for one of those stakeholders. We really need to think about all of them.
Got it. And I have one follow-up question on the paper. So the currently the framework takes 3D mesh. I am currently observing a lot of also research done on like point cloud segmentation as well as integration of PyTorch 3D. Like, what are your thoughts on those?
Yeah, another way to go would be to do just direct segmentation in 3D. And it's just that at that point, 2D was doing a better job in giving us information that we wanted out of the point clouds, and especially in domain transfer situations. But there is no reason why one couldn't do it with the 3D methods.
Nice. And like personally, like I see on Twitter, like every day there are some like state of the art model or some new cutting edge research work. So I want to know your thoughts, like where is the computer vision industry heading, or and like how it might impact AEC, or how we can integrate the latest research?
That is a good question. I think that the computer vision and AEC do care about similar problems. We do care about similar things, but just applying directly what we see in computer vision, just directly in the AC community, it's not always the best way to go, because there are a lot of issues, and computer vision research does stay within some more constrained data situations, where it's not always the case in the AEC industry. So I think that in order to really go forward, we need to include both on the same table, with both the AEC and the computer vision people, to solve these problems. And again, I said we do care about the same kind of problems. So it would be nice to start working together. And that's what me and my collaborators are trying to do with the different colloquiums and conference workshops, etc., to just say, hey, we just care about the same things. And you know what? We have actually environments for you that are harder than the just regular ones. Would you be interested in working together to do something? Something that is practical, of course, but there are always theoretical things to fix within even something that's very applied.
Got it. And is there anything in your career you wish you would have done differently?
Maybe on things, I guess. But there are no, this is what I don't have any regrets. Yeah, it brought me where we are, and I keep learning every day from my mistakes and the things I'm doing wrong. And I'm very thankful to have alongside me some amazing mentors that just, they're there to guide me and to tell me just their thoughts about things in the industry. And it's still a great, yeah, I'm really blessed in a way to have this.
Got it. I have two questions for like advice to students and young professionals. So, what are some research areas from or either on CV, AI, and AEC you would recommend students who are currently looking for their thesis or PhD research work? What are some emerging areas?
Well, I well, are we talking? We're talking about AEC students, right?
Hmm.
Um, there is a reason I'm asking that, because I would I wouldn't advise them to go that way. I would advise them to see what excites them and inspires them in terms of the project they want to work on, of a problem they want to solve. And if AI can help in actually solving it in a better way, and again, better, one has to define it. But if it's possible to actually have an impact, you should look into AI and see what you can do. But I would never go around to see like, oh, this is the hottest topic at this point in AI. Let's use that in order to solve this problem. It should be the other way around.
Yeah, that's a really great piece of advice. And like looking at I'm just thinking from multidisciplinary and future like requirements. It it might be possible that students might need to work with AI models in future or with coding. So, what are some skills that students should start learning that would help them to be more valuable in the industry? Or yeah.
Yeah, this is another good question. I'm gonna share my at least the way I'm thinking of it, my perspective as of right now. It might change in the future, but as of right now, I do not think that everyone has to be an expert in coding and AI, and we shouldn't be asking that from the industry. I think that we shouldn't also be doing a lot of in-house development here and there. I think because it doesn't allow to really take advantage of the power of AI when you're sharing things. So I'm not 100% convinced that in-house solutions can help. Um, so I do think that people who are in the AEC industry and they care about AI, especially the ones that want to do more about innovation and be involved in that front, they need to understand some fundamentals. And I can explain what those fundamentals are, but they don't need to be experts, and they don't need to be able to even code a full-blown neural network and train it in order to be part, understand about innovation, understand what is important for their business, and how to critically think about it, and decide if they want to integrate it or not. What I see a lot in the industry is just a laundry list of AI applications that they're trying to use or create within their house. And shows that we don't have a strategic thinking about it. It's just who is going to try the new next thing first. This is not good necessarily for their business. They need to be able to better understand and critically think, is this going to help us or not? What is the outcome? For example, A lot of people say, hey, we want to document digitally our facilities. Okay, but why? Why do you want to do that? What is the bottom line of that? They cannot answer this question, and this is not good. We need to be able to understand where we're going, what is the goal, to be able to better integrate innovation in our industry. With the class I'm trying to teach, and this time I taught it at ETH Introduction to Computer Vision for AEC industry. I'm trying to build on top of that. I'm trying to essentially to instill this critical computational thinking to new to new professions that are going to come out in a couple of years, and they might become innovation leaders. They just need to know some fundamentals, how things work from input to output, and what are the questions they should be asking. I'm still working on it, but hopefully as years continue, I might be able to do a better job in understanding what exactly is the knowledge that I need to give to the students. We've done some first steps. There's still a lot of work to do in the educational aspect.
I see. I was about to ask the question, like, what are some goals you have in your courses? What are some takeaways for students? And you covered it. So my last question for the session is what's coming next for you
Well, I guess it's what's
in
coming
terms of
next for you
research
all, I
courses?
guess.
Yeah.
Well, in terms of research, I'm working on a few projects right now with students and on my own that I'm not yet in a position to share because it's still pretty early, so I cannot do that. But hopefully soon you'll see something out there. Fingers crossed. We'll see how things go. Research is unpredictable on its own, so we'll see. So just stay tuned about that. In terms of other events that we are planning the second colloquium as a continuation of the first one. I think it's going to be even more exciting. A bit shorter because we understood that it was a little bit long last time. So stay tuned for the second version. We'll soon make an announcement with the topic and the speakers and the dates. So that will happen.
Okay, I have one fun question. So I know you are involved in a lot of communities and do research work and teaching. Like, what are your hobbies, or what do you do in your leisure time?
That is a good question. Leisure time. There are different things. I mean, I have recently also moved, so some of the hobbies that I was doing back in California are not necessarily applicable here. So there is also COVID, so things have changed. But I do like to do creative things in the house and outside. And I also, that could mean either me creating or observing other people's creations, as well as things that have to do with sports and enjoying the nature. Definitely are within the hobbies I care about. I would say traveling, but it's COVID and I haven't done it for a while, so I don't know if it will be anymore on my list.
Nice. Do you miss designing?
I thought about this question a lot the past few years. I'm not sure. I like designing, but I'm not sure I miss the daily life of an architect. And I'm trying to find other ways to get my creativity out there, even if it's within my own research, even if it's just making a presentation or a figure or thinking about it in a way that might be a little bit more creative and out of the box. So I'm trying to still use those skills, but in a different way. Yeah, and I enjoy this daily life more than the other one.
Yeah, I think many times we have a presumption that okay, once you move out of architecture you will miss the creative part, but I foresee a lot of creative aspect in coding, AI, research work, or even outside AC. So if you're creative and interested in design, you'll find that niche in even in other domains. Yeah,
Exactly. Yeah. You can always do a side job and still keep designing. It's just a matter of what works for you and what not. What are your aspirations? But yeah.
Awesome. I think that's it for the session. It was amazing. Thanks a lot for your time and sharing your work
Thank
with
you,
us.
Mayur. Thank you for having me here. I really
Yeah,
enjoyed talking to you.
awesome. Have a nice rest of your day, Iro. Bye bye.
So, bye.